Welcome to today's lesson where we are going to look further at the magnetic field caused by a wire and how it can interact with other magnets. So firstly, we're going to have a quick recap of last lesson, a couple of key concepts. Just pause the video now and think to yourself, what is the shape of the magnetic field around this wire? So it is of course circular, and we use the right hand rule. We put our thumb in the direction of the current and our fingers show the direction of the field, so the arrows will go this way around. Here we have two wires parallel to each other. We have current in the same direction on the left, current in the opposite direction on the right. Think to yourself, are these wires going to attract or repel? Pause the video now, think to yourself. So the ones on the left will attract when the currents are in the same direction, the wires will move closer together, and on the right side they will repel. So we're going to extend our understanding today. We're going to look at what happens if you put a wire in a permanent magnetic field. So here we have a wire, and we can see which direction the current is going. So this is positive and this is negative. We have a magnetic field. So this is a north pole and this is a south pole, and we can see that there is an orange arrow on the wire where it experiences a force. So what is going on? Well, the wire makes a magnetic field around it that's circular, like I said on slide 1. That magnetic field interacts with the permanent magnetic field from the permanent magnets, and if you have two magnetic fields together, they can either attract or repel. And in this case, it's going to repel the wire downwards. So what I suggest you do is a simple diagram of this, and I would suggest you copy these notes. There is a name for this. It's known as the motor effect. So you should add this to your diagram. When a wire carrying a current moves in a magnetic field, it's known as the motor effect. And next lesson, we're going to look at motors in more detail. But this is the most simple motor that we could have, a single piece of wire moving in a field. What direction is it going to move? Well, in order to work that out, we need to use a new rule. But before that, I'm just going to show you a quick video of this actually happening. So here you can see we have a wire, a copper wire that's connected to a power pack, and it's on a scale. And there are magnets here, And at this point in the video, you can see the scale reads 0.0 grams. There is no reading. The power is off. If I press play and we turn the power on, you can see what happens. The reading on the scale increases because there is a force pushing the magnets down because of the interaction of the magnetic fields. The magnetic field around this wire will interact with the permanent magnetic field from these magnets and push the scales down. If we reverse the current, think what would happen to the reading on the scale. If we reverse the current, the magnetic field would flip direction, and therefore the magnets will be pulled upwards and the reading on the scale will be minus 0.39. Let's see what happens when the current is increased, and this reading here tells us what the current is. So the current is now 5.22, and you can see the reading on the balance has gone up. So more current means there's going to be a stronger field and more force. When it's turned off, you can see what happens. It goes back to 0 because there is no current, no field, and no force. Now, this idea can be extended, and we now see a piece of foil in a magnetic field, and we're going to have an alternating current now, and a current that goes back and forwards. So think to yourself, before I play this video, what is going to happen to this piece of foil if the current is changing direction? So you'll be able to see that because the current is continually changing direction, the magnetic field will be continually changing direction, and therefore the direction of force will continually change. It's up, it's down. If we increase the frequency, you can see that the magnetic field changes direction more often, and therefore the force changes direction more often, and it will oscillate up and down. What we have here is essentially a speaker. Okay, so here it's going very fast, about 10 hertz, 10 times a second. If we take it to beyond 20 hertz, it becomes effectively a speaker, and you can hear this really nicely at around 2000 hertz for this particular speaker. You may need to turn up the sound on your computer now. So it's moving so fast that it is pushing the air, but we can't see it. And this is exactly what a speaker is. We don't need to actually learn about speakers in combined science, but I think it's quite a nice demonstration of just how simple speakers are based on really two simple ideas. So how do we work out the direction of the force? Well, we need to use Fleming's left-hand rule. It'll be a good idea to pause the video now and make a quick sketch of this diagram. So what you need to do, you need to get your left hand and you need to put your thumb, your first finger and your second finger at right angles to each other, just like in this picture. And then your thumb represents the motion of the wire, or also it represents the force on the wire, because obviously the direction of the force will mean that the motion is in the same direction. The first finger is the magnetic field, which is north to south. So this is north and this is south here. And the second finger is the current, which is positive to negative. Current goes positive to negative. And remember that if we have a battery, this is positive and this is negative. So let's look at a couple of examples for this. So here we have a diagram. It's the same one we saw before. We have our current going in this direction. So get your second finger and point your current in this direction. This is the magnetic field. So point your fingers in this direction, your first finger, and then you should see that your thumb points down. If your thumb does not point down, you've made a mistake. So start again. If the current is reversed, what would happen? So the current now is going to point in the other direction. So if you use your hand, if you reverse the direction of current, you will see that the direction of the force reverses and the force would be up. Here's another example. You can pause the video now. You can line up your fingers with the arrows in the diagram and convince yourself that you are correct. And you should keep on trying this until you're 100% sure you've got this right, because the first set of questions is going to be you doing this on your own.